With the internal energy equation, let's now consider what some of the non-adiabatic effects can be that we might encounter in fluid dynamics. The internal energy equation is given by d of the internal energy E dt plus p over rho times the divergence of the velocity u. And then we wrote this as either t ds dt, the specific entropy, or as dq dt. And these terms over on the right-hand side, either the TdS dt or the dq, these are the non-adiabatic effects. And we use that terminology because these are the effects where delta S, the change in specific entropy, is not zero. And so if delta S is zero, then we have an adiabatic process. If delta S is not zero, we have non-adiabatic processes. These are driven by the dqs, and so the question is, what are kind of typical dqs that we might encounter in interesting fluid situations? Well, there are sort of three that we're going to classically encounter in astrophysics and in atmospheres. So these dq dt's, they look something like this, broadly speaking. They're either of the form, so let's give a curly brace here for different kinds. They're either of the form of approximately 1 over rho divergence of fluxes. So this is if we have a class of fluxes of thermal energy. And one of these examples is if the flux is equal to, for example, a diffusive flux, something like a kappa grad T, which would be appropriate for something like conduction potentially, or something like radiative transport in a diffusive approximation. We might have it be another diffusion-related term. Our dq might also be something like a 1 over rho grad u, so this is a 2 tensor, grad u, dotted into the stress energy 2 tensor, ij, the viscous stress tensor. And this represents viscous heat, which you can think of as friction, internal friction in a fluid. The fluid rubbing against itself and dissipating motional energy and turning it into internal energy or thermal energy. We'll meet pi ij in more detail as we start learning the viscous Navier-Stokes equations. Now there's another way that we could have a source of heat. We could have what we often refer to as an epsilon term, a generation term. And this usually comes from chemistry. Chemical sources of energy that are releasing energy from the chemical reaction into the internal energy. The classic one for the interiors of stars is that this might actually be a nuclear chemical reaction, something like hydrogen burning to helium, which we may not think of as a chemical process per se, but it's a way of taking constituents and turning them into different constituents and releasing a tremendous amount of energy in the process. To give you an idea of the kind of feel of these epsilon terms in actual astrophysical circumstances, for stars like our sun, these can be very temperature and density dependent. So for a star like our sun, it releases energy using something called the PP chain process. the pp chain, it takes hydrogen. It takes 4 hydrogen, and it turns them into a helium atom plus some anti-electrons that carry off charge. So these are all in an ionized state. So to helium plus 2, it releases a couple of positrons, and it also releases a bunch of photons in sort of the gamma ray energy range. Now, when we're considering at a fluid level, we don't care about the kind of particle level interactions like this. We care about the large scale contributions of these interactions to the fluid itself. And so we might parameterize the pp epsilon process, the pp chain process, as a function of rho and t. Well, the actual functional form you can derive from nuclear physics, but it often becomes helpful to think of it in terms of power laws. The actual functional form's a exponential with some other terms out in front of it, but we can consider the behavior of this around the sort of classical temperatures at which nuclear fusion actually occurs. And so if we think of a power law, so this is not really, a power law is the wrong description for this, but it can give us a lot of intuition. So we're going to use a special symbol here. This is approximately proportional to, which may cause the mathematicians in our audience to just roll over in horror. But it's a good astrophysical term. Approximately approximately proportional to. So this is saying that something is, so approximately, right, or proportional to is saying it kind of has this feel and this sort of scaling, and approximately proportional to with the tilde underneath says it's got this scaling if we're in the right kind of range of temperatures, but if you push this very far, it changes dramatically. So we might show this as a power law, like rho to the alpha and t to some power beta, and for two things coming together. So the pp chain, this shows 4 goes to 1. This actually happens in individual hydrogen plus hydrogen turns into deuterium, and then you collide another hydrogen with that. So it's basically two particle interactions chaining together to give you an overall reaction. So that has a density dependence of 1, and the temperature dependence, we take that by basically fitting the exponential in the regime at which we're doing these temperatures. That's temperatures of sort of 15 million Kelvin. That has a rough power law index of about 4. 4 to 6, really, kind of practically speaking, but 4 for something like our sun. So epsilon p for the sun, it's something like, as a function of rho and t, it's something like, say, rho times t to the 4th. And that'll give you a reasonably good approximation of the source term of energy that operates inside our sun. Different nuclear processes will have different power law dependencies. So the other classic group that we'll run into is that for massive stars on the main sequence, so these are things much more massive than the sun, things that are, a few solar masses up to roughly hundreds of solar masses or so, where we think kind of the upper limit of modern stars is. These use something called the CNO cycle. This is a catalytic burning of hydrogen to helium using CYCLE, using carbon, nitrogen, and oxygen as intermediaries. It's catalytic because you start with some carbon, nitrogen, or oxygen, you add protons onto it, and then you break apart the oxygen and return to carbon. So you basically go here, you build up to a nitrogen, you go here, you build up to an oxygen, and then you come back here with a helium atom also coming off the other side. So you add on hydrogens as you work your way up this chain. It again takes 4 hydrogens to create one helium. All right, so this is a process that's much more temperature sensitive than the solar one. The exponential in this has a factor of like e to the 70 or so, and so here the epsilon has a different power law dependence. Epsilon of the CNO cycle, in a sort of typical massive star at sort of 18 million degrees Kelvin, as a function of rho and t. Well, the density dependence still is density to the 1, but now the temperature dependence is like 20 or so. And this is very, very sensitive, sensitive to the temperature T. This is sensitive in 2 ways. One, T to the 20 is just an absolutely strong scaling with something, but even this power law index of 20, this can change if the temperature of the core of the star varies much from about 16 to 18 million degrees Kelvin. So two of our sources of energy that we might see are epsilon pp, this is like rho t to the 4, and epsilon cno, which is like rho t to the 20. In an atmospheric setting, the ways that you might get chemical interactions with fluid flow are through like the latent heat released by condensation of water. That can be a powerful one. But for most atmospheres, the way that chemistry interacts with fluids is not by directly injecting energy into the internal energy equation, as we've been studying here, but by modifying the opacities and the ability of radiation to get through the fluid. So we're familiar with this on the Earth with carbon dioxide trapping infrared radiation and small amounts of CO2, vastly increasing the ability of the atmosphere to trap infrared. And the same thing happens with many other chemicals for other kinds of light in other kinds of planetary atmospheres. And that's where you'll see that primary feedback.